This is going to be kind of a technical video. I want to show, in class we're going to talk about this sequence where an is 5, and then the way we get the next term is, well, we square the previous term, we add 5, we divide by twice the previous term, and I've just written out some numbers here. It starts with 5, 3, 2 and a third. All these numbers keep going. I've written some decimal approximations. Of course, all these numbers are going to be rational since, we start with rational numbers and we just square them or divide them. And it converges actually pretty quickly to the square root of 5, right? So if we happen to know a decimal approximation for the square root of 5, then we kind of see that that's happening. And I want to sort of fill in the details for this proof. This is a sort of technical proof. Didn't want to do it in class because it's not super enlightening, but it's good to sort of see everything checked. So the claim that we're gonna make to prove this is that the sequence is decreasing, and that all of the terms are bigger than the square root of 5. And so if I kind of rephrase that, that's the same as saying that an is bigger than an plus 1, and then all those are going to be bigger than square root of 5. Right? And so again, where we're going is once we know that this sequence is decreasing and bounded, then it's going to have to converge, right? So there's the monotone convergence theorem that says that all such sequences converge to some limit. And then at the end of this video, we're going to see that that limit is actually the square root of 5. Okay? So how do we do that? Well, we're going to use induction. So induction is good for this because we have a bunch of statements, one for each n. And let's have Pn be the statement that an is greater than an plus 1 is greater than square root of 5. It's kind of a complicated statement. It's saying kind of two different things. But let's just sort of see what happens with P1. So P1 would say that A1 is greater than A2 is greater than square root of 5. We can just plug that in, right? A1 is 5, A2 is 3, 5 is greater than 3, and that's greater than square root of 5, which is, like 2.23. Right? So P1 is true. And so now let's assume that Pn is true. So we're going to suppose that Pn is true. So we're going to assume this. We're going to assume that for that particular number n, an is bigger than an plus 1, and that that's bigger than the square root of 5. And so that's our assumption up here. And now we want to show that Pn plus 1 is true. So I've written down what we want to show. We want to show that, I guess, an plus 1 is bigger than the next term, which is an plus 2, and that's bigger than square root of 5. So we have to prove this in two parts because there are two inequalities. There's the first one and the second one. Let's focus on that boxed inequality. Right? I've kind of switched it around here because I want to kind of simplify the left-hand side, but I want to show that an plus 2 is smaller than the term that came before it. And so, well, remember, after all, we have a formula for an plus 2. It's this fraction. So that's, again, what I want to show. I've put this under the heading want to show. I want to show that this is true. I can cross multiply. Everything's positive, right? Because we're sort of assuming that everything's greater than the square root of 5. I can subtract, and what I get is that I really want to show that a sub n plus 1 is greater than square root of 5, and I know that, right? That's something I know by the induction hypothesis. And so I know this is true by the induction hypothesis, and I hope it's kind of clear to see that all of these steps are reversible. If I started with what I know down here, then I could go back and get to my desired statement that an plus 2 is smaller than an plus 1. And, I think in your proof at this stage, you could write, since these steps are reversible, we have shown that an plus 2 is less than an plus 1 in this case. If that makes you feel uncomfortable, I'll just show you how to do it. We could write these steps forward, right? I could say, since Pn is true, I know that square root of 5 is smaller than an plus 1. I square both sides, I add an plus 1 squared to both sides. I just kind of write those steps backwards, and I just find everything out. Right? So you may want to pause the slide. It'll actually be really good to pause the slide and sort of see where each of these inequalities comes from. Maybe a question on induction I could ask would be, in this context of this proof, why do you know this inequality is true? or why do you know that this inequality is true, or something like that. In any case, we've finished this half of the proof. We've proved that an plus 1 is going to be greater than or equal to an plus 2. And so let's continue. Right? So now we've got to prove this other part. We got to prove that an plus 2 is bigger than the square root of 5. And so we do exactly the same thing. This is going to be equivalent to, we plug in our formula for an plus 2 into the previous one. We cross multiply. We are going to get, we subtract this square root term from both sides. This factors, hooray. And it actually factors as a perfect square, right? So now if we look at this perfect square, we say, well, when is an plus 1 minus square root of 5 all squared going to be positive? Well, the only way it could not be positive would be if it was exactly 0. Because any square number is going to be 0 or bigger. And so, you know, an plus 1 minus square root of 5, that has to be positive. Because our induction hypothesis, let's go back to it, our induction hypothesis says that an plus 1 is strictly greater than the square root of 5. So, let me get rid of my pointer. And so that's gonna follow by our induction hypothesis. So again, all these statements are equivalent. So really, we're okay. But if you really want to, you could go back and sort of rewrite this proof backwards. You could say this is true because we know that this is true by the induction hypothesis. We could rewrite all those steps in reverse order, and in the end we would show that an plus 2 is greater than square root of 5. So at the end of all of this, we've shown that an plus 1 is bigger than an plus 2 is greater than square root of 5, and our proof by induction is complete. So what we've shown is that in this particular sequence, the sequence is decreasing and every term is bigger than the square root of 5. So therefore, an is decreasing, it's bounded, and therefore it converges. Right? So that is great, and we might want to find that limit. And so let's say that the limit is L. We know there's a limit that exists, and so that's what justifies sort of what's about to come. And if we look at this statement, well, it says that the next term is given by the previous term squared plus 5 over 2. Well, if we go towards the limit, we take the limit of the left-hand side and the right-hand side. Well, the limit of the left-hand side has to be L, right? If an converges to L, then, if we just shift the terms by 1, of course, it's still going to converge to L. The right-hand side has to converge to L squared plus 5 over 2L. So that's what I've written down here. And, we can cross multiply. We simplify, we solve for L, we see L has to be plus or minus the square root of 5. All of these terms, it's pretty clear these terms have to stay positive because we start with a positive number and there's never any chance to get anything negative. And so our limit is going to be the square root of 5. And so I think we've rigorously proven now that this sequence converges to the square root of 5. And yeah, thank you for watching. Maybe a question for you to think about in the comments. Is a good question I just thought of when I was making this video, is it would have been a heck of a lot easier for us to show that an is decreasing and that all the terms would say bigger than 0. In fact, as we just said, it's kind of really easy to see that all the terms are bigger than 0 because there's just no way that we could ever get a negative number, right? So why do we go through all this extra work of showing things are greater than the square root of 5? There actually is a reason, and if you go back and look at the proof, maybe you'll see why. That square root of 5 actually came into play at a couple different points in our proof, and if that number had been 0 or really anything other than square root of 5, that proof wouldn't have worked. So thanks for watching, and I will see you in class. Goodbye.